So here PC is indeed twice sine pi over 18, and here it's 1 minus twice sine pi over 18. And here it's approximately 0.7, here is approximately 0.3. But this one gets basically using Keston's argument. Actually, I don't know whether it was rigorously proved, honestly speaking. So there is an argument which can be made rigorous if you do Keston, but basically you get that it's self-dual point by going around this thing. Okay, so naturally means that there are two logical cases to do, because they are self-dual, so it's easier to work with them and it's easier to use self-duality. So far we only have a proof in this case, and I don't know any really good plan to do it for square lattice. So one Sandby-Farah has, well, actually no, Sandby-Farah has a good plan, but so far it turned out to be too difficult. And his plan was to reduce it to the same thing. Okay, so we'll do today the main lemma. So let's start from the Cardis proof that he wanted to move the point on the boundary, and he already assumed conformal invariance. We want to prove conformal invariance, and then of course it would be to our advantage to have points not only on the boundary of the domain but also inside the domain. So the idea is that let's do the same thing as Cardi. So Cardi was doing. So he was having 4 marked points, and the fourth could move on the boundary. And then he was sort of looking at what is the probability that there is a connection between these two sides. So let's just modify a little bit what he does, and let's allow to the fourth point to move inside. So we look at the probability. So this point now can move inside the domain. So he was looking at this probability. We look at that probability. Now basically what was here the event that there is a crossing which separates these 2 points from these two. So we just do the same event, that there is a crossing between the 2 opposite sides of a triangle which separates one vertex and a point inside from the other 2 points. So the theorem which we will prove is that this probability has a conformal invariant scaling limit, which is harmonic. So there is a harmonic conformally invariant scaling limit. Now for an equilateral triangle, it is linear. So for example, if I map it to an equilateral triangle, this picture, and I ask what is the probability that there is a crossing below this point, so it's a linear function in the triangle, which obviously is 0 on the bottom line, because if I'm on the bottom line, there is no crossing below me. And it's obviously 1 at this point, because here there is a good chance that there will be some very small crossing. So it's linear with the boundary values 0, 0, 0, 0, 0, 0, 0 here and 1 here. So it's, in this particular picture, it's just imaginary part divided by square root of 3 over 2. So this actually, this harmonic function, it satisfies, bring out to harmonic discussion, satisfies Dirichlet problem at one point and one arc. But here it satisfies Neumann problem with an angle of 60 degrees. And in principle, you can define this, if you wish, you can define this problem on a triangular lattice. But we'll proceed slightly differently because we'll proceed by looking at harmonic conjugate of this function. And actually here you can observe that there are 3 of them. So there is this, well, there are actually 3 variations of this function. Let's say if this is points A, B, C, A, B, C, A, B, C, you can define function HA, HB, and HC just to be the probabilities that there is a crossing like this, there is a crossing like that, and there is a crossing like this. So they all be linear, but this will be linear like this. This is towards B, this is towards A. As you can see, the sum will be equal to 1 because these are 3 linear functions, which each of them is 0 at 2 vertices and 1 is the other one. And this is actually not a trivial observation. I don't know how to check this besides proving this theorem that if you fix any point, sum of these 3 probabilities is equal to 1. On the boundary it's easy to check. On the boundary it's exactly the observation which, well, it's sort of related to this observation which I made earlier today. Okay. So what we'll do today, we don't have enough time to prove this. What we'll do, we'll observe the key part, we'll observe sort of Laplacian identity, or rather Cauchy-Riemann identity. So the unfortunate difficulty, and it's how it differs from the uniform spanning trio operator and Novak or the Ising model, which is yet to come, is that we don't have exact identity on a lattice. So on a lattice, the function is not exact harmonic. It is harmonic in the scaling limit. On a lattice, there is an exact identity, which, if you look at it carefully, it says that it's harmonic with a small error term, which locally you don't have much control over. But if you sum it over some area, you have very good bounds on this error term. Okay. So this is the function. Let me maybe erase something. What is a good thing? So so let me also, for simplicity, maybe I will denote, so I will put some notation. So I will put, say that tau is the cube root of unity. So it's e to the power I 120 degrees. And I will maybe denote these functions for simplicity h1, h tau, and h tau squared, sort of to see that they have cyclic symmetry, that each of them you get by rotating by 120 degrees. Then just the formula, then instead of 3 formula, I have to write 1 with tau in the index. And maybe running a little bit fast, so of course, well, I mean, a function can't have 2 harmonic conjugates. So these 3 functions will be harmonic conjugate in the following sense. So they will be projections of analytic function on 3 vectors, on 3 cube roots of unity. But of course, these three vectors are linearly dependent. So projections of analytic functions on them are also linearly dependent. So any two of them can be any one of them can be reconstructed from two other ones. So these three functions, they are up to a constant projection of a single analytic function on three group units of unity. And in these coordinates, just function z. You project it on imaginary part, you get real. On imaginary line, you get linear function. You project it on this line, you get this linear function. In an arbitrary domain, you take z in an equilateral triangle, map it conformally, and then you project it on these three vectors, and you get the values of these three functions. So in a sense, they are harmonic conjugates, but if you want the exact harmonic conjugate in the usual basis we use, not in this one, then for the first function, you have to take the difference of these two divided by square root of 3. So, and then you get exact harmonic conjugate. Okay. Now, so the sort of a key lemma or key observation. Let's once again I do this function. So we take domain. So we take a discrete domain on a triangular lattice. On hexagonal if you wish, so we do side percolation. So this is the lattice. Mark 3 boundary points. Well, let's say A1, A tau squared. Counterclockwise. For Z, a center of triangle, so we define our functions on centers of triangles. So this is Z. H, let's say H1 of Z is the probability that there is a crossing. Again, where is my yellow chalk? So there is a crossing from this side and so on and so on. So it goes something like that. So there is a crossing from the side 1 tau to the side tau squared 1. Separating Z from tau squared. And if you want to define all the three functions, then you just try that you just instead of 1 you multiply by something to rotate H alpha, and then you write alpha tau alpha tau squared alpha tau squared. So where you can put alpha 1 tau squared. So we have three functions like that. So we define it, of course, not at vertices of triangular lattice, but at the centers of triangle, so that it's clear whether the crossing is below or above. Now there is a simple combinatorial observation. Well, there will be in a second simple combinatorial observation. But what we want to do, we want to show that our function is harmonic or analytic. So we want to check either that Laplacian is 0 or that Cauchy-Riemann equations are satisfied. So we want to differentiate it for a start. So what we do, we want to differentiate it. Let's examine derivative in the direction beta of our function h alpha of z. Now, basically, how does this look like? Let me just draw two big pictures. So this is probability that z is above the crossing minus, so let's again, let me just do, so this is point z, and this is the vector beta, so we get another point z prime. So z prime is z plus beta, and we want to estimate the difference between them. So it's probability that z above, or minus probability that z prime is above, or vice versa. So it's h alpha of z prime minus h alpha of z. So in the future, if we want to approximate the usual derivatives, we have to divide by the length of the vector beta. So far we don't divide it for simplicity, but in the future we'll have to divide by the length of vector beta so that it will be something resembling the usual derivative. And so this probability that z prime is above crossing and this probability that z is above crossing, and that you can write as the same thing as for uniform spanning tree, that z prime is above, z is not, minus probability that z is above, z prime is not. So this is exactly the same thing. We don't use any properties of our model. We just draw pictures, and let me just draw it. What corresponds to these probability events. So we have this marked vertex alpha, alpha tau squared, alpha tau squared. And we have this piece we are interested in. Z prime, z prime. So what does it mean that z prime is above? It means that below it there is a crossing. But it's not below z. So the crossing has to pass between them. So there is a crossing which goes something like this. It arrives at this point, uses this edge, and then goes off. But there is no crossing below. And then there is this duality property of percolation, which probably was discussed in the usual course. But the fact that there is no such crossing, it means that there is a crossing of opposite color which goes like this. So it's a remark. Use duality. So duality says that so you always have either this, so not this, is the same as having a crossing in the opposite color horizontally. So that was discussed in the course of percolation. Yes? So the difficulty, if you try to do this in the square lattice, you already run into the difficulty because here you shift to the dual lattice. And in this case, you don't shift. You just are in the same lattice. So there is this, sometimes it's called like game of hex lemma. So game of hex was invented by some Danish game inventor and then independently invented by John Nash, the famous John Nash, and in Princeton I think you still have in common room a piece which he made out of cardboard himself. So the game of hex is played on a hexagonal board. So there is a hexagonal board, and two players, they have hexagons of two colors. Let's say yellow and blue. And then the goal of one player is to build a yellow path in one direction. So one player wants to build a yellow path like this, and another player wants to build a blue path like that. And they put hexagons until one of them does his job or the whole board is filled. So the game of hex lemma says that exactly one of them will win. So when you fill everything with blue and yellow hexagons, either there will be yellow crossing in this direction or there will be blue crossing the other way around. Why? Because suppose that there is a yellow crossing in this direction. Then obviously there is no blue sideways because there is an obstruction. Now suppose there is no yellow crossing. Then it means that there is obstruction. Why? Because just take everything you can reach with yellow from the right side and go as far as you can. Either you reach this side, or if you don't, the perimeter of it is a blue crossing. So it's just a simple topological statement, discrete version of Jordan's theorem, so to say. Well, so we use this, and we use duality for a very specific rectangle here. So we use it for the following rectangle. So it's 1/2 of our domain, then this thing, then this thing, and then there is this point. So this is our rectangle. And what I'm claiming is that either there is a yellow crossing like this, or there is a blue crossing like that. So it's kind of degenerate rectangle, so one of its sides is a single point. So this is a duality observation. Is it clear? So this is so far so good. So it's exactly the same. It would be the same. You can do it for Ising model. You can do it for any covering of a plane. We only used that we have a triangulation. So if you have quadrangulation, this is no longer true, because in quadrangulation you have chessboard coverings where neither of the covers has a crossing. So this is you use indeed this triangulation. Okay, now what will be this picture? It's the same as in uniform spanning tree. It's with a twist, because here Z prime was above and Z below. Here it should be the other way around. So it means that our thing has to make a twist. So it has to go like this. So you might think that this picture is less likely. Well, for this size, yes. But if size is very small, the generic picture, if it occurs, it will win infinitely many times. Well, not infinitely, but logarithmic number of times. So if it's scale n, it will win log n times. So it will be not this picture or this, but here you will have even number of twists and here odd number of twists with id on O and id and even being very large numbers. So you shouldn't think that this is a perverse picture and this is a normal one. I mean, both of them, they're equally normal. So it's okay. So far, so good. Doesn't do us any good up to now. And then there is a trick which does us good, and the trick is due. So it was, to the best of my knowledge, in this context, it first, well, not in the context of conformal invariance, but it was used for playing with arms by Eisenman, Duplantier, and Aharone. So in physics papers, it's not always that they have alphabetical order of names. And so they had made an observation. Well, it's kind of, so you discussed already, when you discussed Russo-Seymour-Welsh theory, you probably discussed things like that we choose the lowest crossing of yellow color. It depends only on what is below this. And then we play with the rest. For example, what we can do, we can change the color to the negative and probabilities remain. So for example, probability of having 2 yellow crossings is the same as probability of having 1 yellow crossing and 1 blue. Why? You choose the lowest yellow crossing, then there is a second yellow, but you can flip it to negative. So it's the same then as having second which is in blue, because flipping is allowed because probability is 1/2. So things like that, there are several proofs of Russo-Seymour-Welsh. I don't know which one you have seen, but most of them, they use sort of a trickery that you condition on lowest crossing and you play with it. And it turns out that this color flipping trickery, it can be used here to show that you can change colors of these arms. So you can do the same picture. So let me. And for example, what you can do the arms which will be, let me say, like that. So I will show it in a second. But there is observation of Azimuth-Duplantier de Haron that you can change the colors of the arms and probability is the same. And here you immediately see that there is something interesting, because what we had derivative in this direction. But now we have a similar picture, but in a different direction. So we have derivative in a direction rotated by 120 degrees. But we differentiate a different function. We differentiate not function alpha, but function alpha tau. And I mean, the first, of course, guess would be that this would be derivative in the direction tau beta of function tau alpha at point z. And it so looks on this picture that we just rotated the vector, we just rotated the thing, and we only have to work out the second picture. But there is a small problem when we work out the second picture and change the colors of the arms there. So again, we change them in the same way. Let me just see how does it work. So we'll change them in the same way. So this goes here. This goes there, and that goes here. And the vector then, let me see, did I screw it up? I wanted yeah, everything is correct. So the vector was like that. Yes, the vector was like this. Yeah, okay, so the vector was like that, and now it is like this. Okay, so does anyone see a problem? So above we were playing with one, so to say, rhombus. So we started with an edge through which we jump. And then in one case we added arm on one side of the rhombus. On the other case we added the arm on the other side of rhombus. Now do we play here with the same rhombus or not? So it should be then this rhombus. But no, in this picture we do it differently. We do it with a rhombus which is quite alike, but shifted but by one step. So you see the problem is that this vector, we rotated here around point Z, which is our main reference point. But on the second picture, we rotated it around Z prime, not around Z. So if it were around Z, we would have had just the second half of this derivative and everything would be nice and we would get this thing. But the second thing is shifted by one step. So it's, I would just formulate lemma with a approximate sign and then make a few remarks. So I still have an obligation to prove that you can change the color of arms. I will do this at the end. But first I want to make a remark why it is not that bad. So why it is not that bad? So so what happens is that we wrote our probability as difference of two things. Our derivative is difference of two things at one place. Now when we do this rotation, it's difference of two things, but one of them is shifted a little bit. Now, how do we pass to a limit with analytic functions? It's hard to pass to a limit with local statements. Check that Laplacian of a limit is still 0, or that the Cauchy-Riemann is still 0. It's easier to work with global statements like contour integral is 0. How do you get contour integrals from Cauchy-Riemann? You integrate Cauchy-Riemann equation over an area, and then you get contour integral of the perimeter of the area. So if I start integrating this identity, which is almost like Cauchy-Riemann, only I rotate by 120 degrees, the fact that the second thing is shifted by one lattice step is no longer that important, because in the bulk, inside the contour, I will still get every place only from a neighbor, not from itself. So if this and this goes within the space inside a contour, say big triangle of size 100, this goes in the same triangle, and this goes in the same triangle shifted by one step. So essentially what means that I get an error term which is just the perimeter, part of the perimeter of this triangle, so it's much smaller than what I am dealing with. So we shouldn't worry too much, because the error there will be an error, but it will be smaller than the thing we're dealing with when we anyway do our proof, and that we'll see later. So it's worrisome, but it's not. So we have an exact identity, but it's for some combinatorial probabilities. This does not give us exact identity for our derivatives. So let's maybe write it more precisely. So let me write that derivative b of h alpha. So this will be the lemma. Derivative b of h alpha. We written as a difference of two things. Bless you. So let me just denote them as d plus beta h alpha of z minus d minus beta h alpha of z. So it's probability of such thing minus probability of such thing. So it's and then this is equal to d tau beta plus h tau alpha of z, so everything is okay, minus d tau beta minus h tau alpha, but the point in question now has shifted. So the point is no longer sorry. So the point, so it was supposed, let me see, so what do we get? So it's z, so we shifted the point by such vector, so we shifted the point by this vector, and so this, which vector we shifted it by, so instead of, yeah, so we shifted it by one lattice side in this sideways, which was, no, it's second, it should be by beta, not by, so we, let me think. So we rotate, yeah, okay, so if it were this rhombus, everything would have been fine, but we have a rhombus which is shifted by one step instead. So it's instead of point z, we have, so instead of point z, we have, okay, let me draw a bigger picture. Okay, so it's, so there is this point, where was this z, and instead we have this point, and this was the vector beta. So this point is not vector beta, is vector beta rotated by how many degrees is that? 30 degrees, yeah, 30 degrees. So it's z plus beta e to the power minus I pi over 6. Well, maybe I just do it z tilde, I just denote z tilde, this z tilde, where z tilde is z plus beta times e to the power minus I pi over 6. So we shift in this lattice by one step. Which is approximately is equal to z plus beta e to the power minus I pi over 6. So essentially we will just be using contour integrals by integrating these two over the area, but there is an error term here which will almost disappear because we sum everything with a shift. Okay. So this is one explanation. Yeah, what else did I want to say in the remaining 5 minutes? Well, I wanted to say that in reality, of course, so the derivative of a function, if a function is nice harmonic, is like a constant, of order of a constant. Since we didn't divide by the lattice step, we didn't divide by beta, the order of this thing, if the lattice step is, say, epsilon, the order of this thing should be around epsilon. But the order of these two things are a bit bigger. So a posteriori with the CLE you can calculate the probability that you have 3 arms, and each of these things will have the order epsilon to the power 2/3. So if you look at these things and you expand them in a power series, the first term will be epsilon to the power 2/3, and it will look at the geometry of the plane, and it will cancel out in both of them. And the next term of order epsilon, it will already see the boundary of the domain, and when you subtract, it will give us some property of the domain. So this is another observation. The other, also what I said, that normally these arms will twist around many times, so they will spiral around, so there will be indeed pictures like that. Okay, now I need to prove the cover flipping thing. So the cover flipping. So suppose we have these three arms, like on that picture. Now, what you can do, and this is, for this you use the arms of different color, you can use, well, normally if I would have had only yellow arm, I couldn't have chosen the counterclockwise most, because I just keep rotating it around counterclockwise, and it's not like choosing the, you can easily choose the lowest in a rectangle, but counterclockwise most on a dial of a watch, you cannot, because you keep rotating around. But there is a natural barrier, this blue arm. So there is a counterclockwise most yellow, and there is a clockwise most blue, because they eventually will bump into each other. So choose counterclockwise, choose counterclockwise most yellow and clockwise most blue. Now they only depend on the space between them. So these two arms only depend on the space between them. If I change something here, their location doesn't change, only changing inside. So they only depend on, let's say, K, which is space between them. Which means that we are free to resample the rest. So we can resample the rest. So apply negative to the rest. So applying the negative, which is exchanges the two colors, keeps probability the same, because P is equal to 1 minus P is equal to 1/2. It means that this preserves probability. So probability of this picture would be the same as probability of the same picture where I resampled the rest and hence have switched the color of this arm. And then you resum over all conditioned parts K, and you are done. So if you condition on part K, you can change the color of this arm, because you can just flip everything to negative, probabilities are preserved. And then you sum over all conditioned parts K, and you get that the probabilities of three arms are the same. So we have seen similar arguments when you did Russo-Seymour-Welch theory. So it's a very powerful tool in percolation, but it's of course very dangerous to use, because you have to condition on something from which what you work with is independent. And in the line of work, when you try to prove something, half of the times you try to condition on something which is not independent, and then you end up either getting a contradiction or proving great theorem, and and then finding a mistake. And it's not like everyone does that, so one has to be careful about it. Okay, so we did today the main lemma. Now it's basically technical things, and the question is just to do them in an elegant and easy way as far as possible. But essentially, what we have a Cauchy-Riemann equation. But normal Cauchy-Riemann equation, it says that projection of functions on two lines at 90 degrees, derivative of one in direction beta is derivative of other in direction rotated by 90 degrees. Here we have projection of function on two lines at 120 degrees, so derivatives there, you have also rotate the direction by 120 degrees, and we have three of them. So it's the only, and we naturally let here, because we work not on a square lattice but on a triangular lattice, but also our model somehow has built-in threefold symmetry because it's related to SLE6. Okay, I think we'll finish the proof. So Monday at 9:15 there is a lecture which is followed by exercises for Nicolas Courien's course. Okay, thanks.